Good afternoon, everybody, and welcome to this webinar titled Simulating Eddy Current Braking Systems in EMS for SolidWorks. My name is Arvind Krishnan, and I will be your presenter today. And on behalf of EMWorks, I would like to welcome you all and thank you for attending today's webinar. Let me first go over the agenda that we have for this short webinar. We're going to talk a little bit about a promotion. Then we will jump into the eddy current braking. Then I'm going to show you a live demonstration of an eddy current braking example. Then we will talk about the workflow that one needs to adopt in SolidWorks and EMS to accomplish problems such as eddy current braking. Then finally, we will talk about the bundling of our product and how should you decide to purchase you can go about. And then we will also reserve some time for Q&A. So with regards to Q&A, just a few bookkeeping items. As we progress through this webinar, you might probably need to ask me a question. So what I encourage you to do is use the chat option through the GoToMeeting. So you can chat with us and please type in your questions. And towards the end of this webinar, I'll try my best to answer some or all of them. Meanwhile, I would also like to let you know that this webinar will be recorded and a recording will be sent to you. So please feel free to share this recording with your colleague or colleagues who could not attend today. Okay, so let me just start with a special offer that I have from my sales team here. And this applies to all webinar viewers. And we are offering a 40% discount on EMS Magnetic with Motion add-on. And this particular offer is valid until December 25th. And as we go towards this webinar and I talk about the bundling, it'll become clear what the offer is and what you need. Basically, everything that you need to do eddy current braking systems and simulate them in SolidWorks and EMS, that module that you need is up for an offer valid until December 25th, 2019. Now let me just go ahead and start this webinar and by explaining to you some basic concepts of eddy current braking, really how it is accomplished. Okay. As far as simulation is concerned, we need to do transient magnetic simulation coupled to motion to simulate eddy current braking systems. Basically, it's a multiphysics type of simulation that involves magnetics, motion. Okay. Now we can easily accomplish these with EMS and SolidWorks. Okay. Now let us understand briefly how this eddy current braking systems in general work. Okay. First of all, eddy current braking systems work on conductor materials. So if you have conducting materials, the better the conductor, the more effective is the braking system. So if you have conductive materials that are moving and you suddenly introduce a magnetic field, then what happens is eddy currents are induced in these conducting materials. Now these eddy currents are set up in such a way that it opposes the original magnetic field which induces the eddy current. As a result of these two opposing magnetic field, the motion of the moving conductor gets affected. Basically, it experiences a retarding force, and this retarding force is responsible for braking or slowing down the moving component. Now, for example, I have something on my right. You can see a disc that is partially in green and partially in brown at the top right hand corner image. Now imagine that this is a disc that is rotating at a particular RPM. Now if I suddenly introduce a set of magnets, as you see above, close to this disc, then what happens is eddy currents are induced in this disc, and these eddy currents is responsible for creating a retarding torque on the rotating disc, and this slows down the disc. And we will actually use this example in the demonstration. Now when it comes to EMS, it helps you to visualize the magnitude and the distribution of these eddy currents. It also helps you to understand what is the total magnetic flux density in the vicinity of these moving conductors. And finally, it, along with SOLIDWORKS Motion, it helps you to determine the response of the moving component. Basically, what I mean by response is really a time response. The displacement, velocity, acceleration, etc. versus time can be studied, and you can understand how long it takes for a spinning disk to reduce its speed or come to a standstill, so on. Okay. So now that we have a little bit understanding of how eddy braking works, let me use this opportunity to go to SolidWorks and EMS and show you, using a live demonstration, how the product can be used to do eddy current braking. Okay. There are some objectives with respect to this particular simulation. The first objective is for us to determine the angular velocity of the spinning disk as a function of time. We would also like to plot how the torque, or in this case the braking torque, behaves as a function of time. And finally, we want to visualize the magnetic flux density, the eddy currents, etc. in the plates. Okay. So with this, let me just quickly change my screen to SolidWorks. And here I have the model that we are going to analyze. Now this particular model has been generated inside SolidWorks 3D CAD. And that's really the principle of EMS. EMS is a add-in product to SolidWorks. It is a gold certified add-in product to SolidWorks. And the value it delivers to the users of SolidWorks is that you can do your electric and magnetic simulations right inside SolidWorks. Now, for example, here I've created an assembly. Now, this is an assembly which first consists of a back iron part. Then it consists of a set of magnets here. And then we have a spinning dish, a disc. Now, the objective is really to introduce these magnets on top of this spinning disc and see how long it takes for the disc to reduce its velocity or its angular velocity. Now to accomplish this, we need to go ahead to EMS tab. Now EMS tab is a location where you will organize all your magnetic studies. Now to start a simulation, the first thing one needs to do is to right click and create what is called as a study. In EMS, all simulations are organized as studies. Okay. Now we have several different studies that are applicable, but what we would use for eddy current braking is the transient magnetic study. Now while this is being brought up, let me take the opportunity to explain to you all the different study types that we have in EMS. We have the magnetostatic study. If you have just permanent magnets or DC currents, then one would use magnetostatic. If you are dealing with AC currents, then we can use AC magnetic simulation. And when you're dealing with any kind of motion transients involved both in the magnetic field, which is produced due to a rotating magnetic field, as in this case, or it is produced due to a time varying current or so on, then you would use a transient magnetic study. So for eddy current braking, which actually involves computation of eddy currents, and eddy currents are induced because of the motion in the vicinity of the magnetic field, we would use a transient magnetic simulation. Now, EMS also allows you to couple to several multiphysics domains. Now, for this particular example, we would like to couple this to a motion simulation. But EMS also allows you to couple to circuits or to thermal. Once you create a study, EMS creates what is known as a study tree, as you see here. Now, in this study tree, we march from top to bottom, and this will bring about the subsequent steps we need to follow to set up the simulation. The first step we need to do here is really to look at the properties of the study. So let's go ahead to the properties of an existing study that I created. As I mentioned earlier, you can couple to motion. Here you have to specify the SOLIDWORKS Motion study that was already created for us. Now let's go to the SOLIDWORKS Motion study. Now, as far as the SOLIDWORKS Motion is concerned, we need to do a few things for it to couple with EMS. The first thing we need to do is set a total time for the motion and electromagnetic simulation. In this particular case, I'm interested in studying if the magnet arrangement is able to substantially reduce the RPM of my rotating disc in about 20 milliseconds. So the total time that I'm going to be using for this simulation is 20 milliseconds. The next thing that I need to do is I need to apply a braking torque to the problem, to actually the spinning disc. In this case, I'm applying a braking torque to the spinning disc, but I'm actually giving a value of 0 Newton meter. Now, this value is nothing but a placeholder. Now, this is where the real torque calculated by the magnetic simulation, the transient magnetic simulation, will be handed over to SOLIDWORKS Motion to actually run the motion simulation. So basically, these are two steps that one needs to do in SOLIDWORKS Motion. Now that we have got that done, let's just revert back to our study here. The first thing that one needs to do is set up the materials for the various components. Now, the back iron core is made of mild steel. The copper disc, as the name suggests, is made of copper. And to create any material in EMS, all you need to do is right click and say apply material. Now, EMS has its own material library, as you see here, which are neatly categorized into commonly used materials. We have ferromagnetic materials, we have permanent magnets, and so on. Now, this is a fully customizable material library. One can create their own material libraries inside EMS or use the material library that comes default with the program. Now, after the copper, then we are going to examine the magnets. Now, each of these magnets are made of neodymium. And as you see here, the direction of the magnets are being indicated by the arrow. Now, to actually look at the direction of a magnet, all you need to do is right click on the magnet and go to coercivity direction. Now, this is where you will be allowed to set the direction of the magnet. Now, magnets can be set either using the global SOLIDWORKS coordinate system, or you can create local SOLIDWORKS coordinate systems and use them. All three commonly used coordinate systems like Cartesian, cylindrical, and spherical can be used to create the direction of the magnet. Now, once all the magnet directions have been created, you can go ahead and then request the program to compute the torque acting on the rotating disc. Here, the torque acting is computed using a technique known as virtual work. So when we request the torque, we also need to tell that please transfer this torque to the SOLIDWORKS Motion torque 1, because this is the torque that will take the placeholder of 0 that we set up in SOLIDWORKS Motion. Now that's all we need to do to take care of defining the simulation. There are just a couple of things that I want to bring to your attention. There is something called the air geometry. Now every magnetic simulation requires us to create what is known as the air geometry, and the air geometry can be defined simply in SOLIDWORKS by just creating an arbitrary solid around your model. In this case, I have created a cylindrical solid around the model to define the air geometry. An air geometry is a prerequisite for doing any magnetic simulation. So let me go ahead and hide it because we don't really need it right now. And EMS uses what is known as a finite element method. And one of the main things in the finite element method is actually a finite element mesh. EMS creates a finite element mesh automatically, as you see here, and this mesh is optimized and can be used for the solving purpose. So let me go ahead and hide the mesh. Now, prior to this webinar, I've already solved this particular example. So let us jump quickly into the results and see what meaningful results one can obtain using EMS. The first set of results that one can obtain using EMS is really what we call as a quantitative set of results. Now, if I open the result table, then I actually have many things organized here. So I have the torque, I have the angle, the displacement, the angular displacement, I have the angular velocity, and I have the angular acceleration. Let's first look at the torque. Torque we need is torque about the z-axis, and let us understand how that varies with time. As you see here, at time step 0 there is no torque, and as the model starts to rotate, a high negative or a retarding torque is actually created, and as a result of this high retarding torque, the rotating disc starts to slow down. But as the rotating disc slows down, then the torque created is not that high. So that's how really the work. So you can get a function of torque versus time in EMS. The next thing that we can do is really to study the angular velocity versus time. So let's go ahead and plot the angular velocity versus time. As you can see here, it starts at around 6,000 degrees per second, that's or 1000 RPM. That's the speed with which the disk was initially rotating, but due to this retarding torque, the speed drastically reduces to less than 1000 RPM within 20 milliseconds. So the objective here, if you remember, is to see how much the speed reduces or how much of the braking is achieved in 20 milliseconds. And we know that at 20 milliseconds, the speed comes to 1/6 of the initial speed, or close to about, or even less than 1000 degrees per second. So the angular velocity and the torque can be studied, and these are called as quantitative measures. Then we can get some qualitative plots in EMS. For example, one can study the magnetic flux density in the model. As you can see here, the magnetic flux density at different components can be studied as a 3D plot, and you can visualize the values here. And you can also go ahead and do what we call as a section plot to see, really look at the magnetic flux density inside the model. So one can do a section plot at various through various sections. So here I've created a section in the XZ plane, which helps me to understand the magnetic flux density in the various components in the model. Okay. Now this magnetic flux density can also be visualized as a vector plot. So for example, EMS allows me to look at the magnetic flux density from the magnets as vector plots. You can see how the magnetic flux density vectors are distributed throughout the model. Next, the most important thing for this particular application is really the current density. This is the plot of the current density. Because we are interested in just the current density in the rotating disk, so let me show the current density only on the rotating disk. Now this is a current density, say after about 5 milliseconds, how the eddy currents are formed in the rotating disk. And these eddy currents and its value in amps per meter squared is there. These eddy currents are largely responsible for the retardation or deceleration of the spinning disk. Now, one can also study the same eddy currents as vectors. As you see here, you can see the vectors, the eddy current vectors. And if you actually look at the direction of the vectors, and you can clearly see how the eddy currents are opposing the applied magnetic field due to the magnets on top. Okay. Now, again, as a recap, we were able to get quantitatively the results, such as how long does it take for the speed to reduce, or what is the reduction in the speed after a particular time. We can see how the torque varies as a function of time, and we can also qualitatively get an idea of the magnetic field in our in the system, and also the eddy currents produced on the rotating disk. So this is really in a nutshell, if I can explain how eddy current braking is achieved in EMS. With this, let me just jump back to my PowerPoint. So as you can see, we had three objectives for this demonstration. We wanted to determine the angular velocity and torque as a function of time, which we did. And we also wanted to understand the magnitude and the direction of the eddy currents induced, which we also saw as a plot in EMS. This demonstration, by the way, is not a very comprehensive demonstration of all the features of EMS product. So to know more about that, you can visit our YouTube channel, and there are more places where you can learn about our products, or simply give us a call. We'll be happy to schedule a one-on-one live demonstration where we can go in detail. Now, let me just recap some of the workflow that you saw in the demonstration that I used. First thing that we need to do is we need to create the model inside SolidWorks. Since most of you are users of SolidWorks, that would really be a easier task. Then one needs to set up a motion simulation inside SolidWorks. Basically, the motion simulation gives the model, the disk, an initial angular velocity, or an RPM. Okay. Then we need to create a transient magnetic simulation and do a multiphysics coupling to SolidWorks Motion using EMS. We assign materials, then we apply the direction for the magnets, then we also tell the program to calculate the eddy currents on the moving components as well as the torque on the moving components. Finally, we run the simulation, and then we visualize the results in EMS. Now let us see how EMS products are bundled. If you really look at it, there are two main types of simulation bundling available in EMS. It's the EMS electric and EMS magnetic. The EMS electric contains electrostatic, AC, and electric conduction solvers, and the EMS magnetic consists of magnetostatic, AC magnetic, and transient solvers. EMS allows us to do a lot of multiphysics simulation, and these are packaged as add-on products. You can couple to thermal, motion, linear static simulation, as well as circuits in EMS. And finally, EMS supports both activation and network-based license. Now, to do eddy current simulation, what kind of package do you need? If you remember, we use transient magnetic and we coupled to motion analysis. So what we need is EMS magnetic and coupling to motion. That's the bundle that you would need to do eddy current braking systems and similar type of applications. This is a comprehensive slide that talks about all possible applications using EMS. EMS is used to do electromechanical, power electronics type of problems where one can study motors, generators, actuators, solenoids, magnetic levitation, coils, transformers, bus bars, insulators, etc. All of these are low frequency DC to a few hundred megahertz type of applications that one can study using EMS product. By the way, EMS was the product that I showed you today. We also have another product called high frequency, called HFWorks, which is mainly used for high frequency. When we are talking about several hundred or thousands of megahertz and gigahertz wavelength model, mainly used for RF and microwave applications. We have other webinars dedicated to this product, so I will not go over much about this. But for more details, you can always consult our website, emworks.com. So the key industries that we cover are all the way from aerospace, transportation, consumer goods, energy, high technology, as well as defense. Now again, as a recap for some of the viewers and registrants for today, we will offer a 40% discount on EMS magnetic with motion add-in, and this offer is valid until December 25th, 2019. So please contact us, sales@emworks.com, to know more about this, and we'll be very happy to help you out with this should you need such capabilities before this year. And finally, on behalf of EMWorks, I would like to thank you all for attending this webinar. Now I will send you a link to this webinar recording so you can watch it again at leisure, or you can share it with your colleagues. Please visit us at emworks.com to know more about our products and the application areas. And a lot of YouTube videos are also available in the EMWorks YouTube channel, and you can get comprehensive demonstration videos, also access past webinars at this location. With this, we would like to thank you all for attending today's webinar, and please contact us via emworks.com or sales@emworks.com should you need further questions or queries. And please don't forget to visit our YouTube channel as well as our website. Thank you very much and have a nice day.